And until also the higher order bits are read, the ADC is locked out. So you should make sure to read this particular register as well. That's very important. But if you're only interested in 8-bit conversion, which we're also will be doing in some of our assignments, then in that particular case we can set the ADLAR to 1. Because now we're just reading the ADC H, and that has all the 8 most significant bits of our conversion. So that's pretty cool. And then we don't need to read the ADC L. The ADC is not locked out, it continues. So that's really nice. So these are the two options. So let's have a look at some more registers. So, and then after that I will show you some code where things come together. We'll go back and forth in slides probably. So here we have a control register with several positions. So let's have a look at those. So this particular position, ADEN, is the analog converter enabled bit. So you want to set this bit to 1 if you actually want to do a conversion. So you would like to enable this ADC apparatus that the MCU controller has, right? Then this next bit, ADSC, well, you want to start the analog to digital conversion if it is set to 1. So that's what you need to do. So if you want to do the conversion and set that to 1. So we'll be doing that in our program. And then a conversion is started for you. And once it's done, it's set back to 0 when done. So what can you do with that? Well, you can then pull the ADSC. So I set it to 1. And then, for example, I have a while loop that checks whether this position, the bit at this position, when this gets back to 0. And once it's back to 0, I know that the conversion is completed. Now you could also pull the interrupt flag. So there's the interrupt flag that's right over here, because the interrupt flag will be set to 1 if the conversion has finished. And actually, it will activate the corresponding interrupt service routine if you would have enabled the interrupt. So we'll play with all of this obviously. So here it is again. ADIF is the flag, the interrupt flag, and the interrupt flag will be set when a conversion is done, and it will trigger on an interrupt if the IDE is also set, right? So the interrupt will be triggered if you have enabled the interrupt. So we have to write an interrupt service routine for that. Alright, so make sure to not mess with this flag. That's very important. And that means that when you are manipulating this particular register, you should be very careful to not touch this flag. So it's much better to, for example, if you want to set a bit like ADAC in here, to do it with the OR instruction, so that you truly only manipulate this particular bit and set that to 1. If you want, and you would like to do that to start a conversion. Okay. Now, the ADIE, again, that's the AD interrupt enable. So we'll write an ISR for that. The ADate allows 1 out of 8 selected events, it's over here, to trigger the ADC converter. So we'll come to that into the next slide. So there can be different types of events that could trigger the IDC converter to start a conversion. We will not be using that, but it's nice to see that it is possible. And it's coupled with the CSRB register, the other control register, that indicates which 1 out of the 8 selected events you would like to use. So let me explain in a moment. But first, the prescaler that I was talking about earlier, that we will want to set to 128, remember, for a 16 megahertz CPU clock, needs to be put in these 3 positions, the ADPS2 to the ADPS0. Alright, so again, if I set this particular bit to 1, then the ADC converter is going to have a look at what you wrote here for those 3 bits. And here's a table. You could, for example, have a counter that on an overflow, in this particular case, the timer 0 overflow, if that happens, then a conversion takes place. And the next time it overflows, again a conversion takes place. So you could create a nice mechanism where you effectively set up a timer 0, you initialize it, and then at a periodic precise intervals you're actually doing a conversion. And for example, if you then have enabled the interrupt service routine for the conversion, you can catch those conversions in that interrupt service routine and display or compute with that however you like. So this is quite an interesting, powerful mechanism. So I hope you will remember that, because I'm sure if you would do something more complex with ADC converters, more complex than what we will be doing, you certainly would like to have a look at this table to see what you, or how you could implement these conversions in a nice, reliable, specific, precise way. So rather than using software counters, for example, to implement it with this mechanism is very reliable and precise. Alright, so let's have a look at how you would write a program. So this is actually what you will be using. It's the kind of the template that you will be using. So we're going to use the UART here, but important is that we have a couple of global variables that we're going to use to display the voltage that we're going to read. The actual value of the voltage we put into a variable called voltage, and we have some A in and A in low that we'll talk about in a moment. And the idea is that we will write this particular string, character string, right, out over the UART. So here is a main program, and what are we doing? So what do you so first of all, we're going to do some initializations. Say we want to have ADC1 as an input to our analog to digital conversion. Well, I need to make sure I always have the directional register set properly. I would like to initialize the UART, and then it comes, right? So here ADLAR is set to 1, and we're going to do the left, so that uses the left adjusted result in ADCH. So we will have an 8-bit precision. That's what we're going to use. We want to set the input voltage to ADC1, and that means that the mux needs to be set to 0001, and that's what we do here. So this particular component talks about the input voltage, where it comes from, and this talks about, once it is measured, how is that representation being stored. And in this particular way, the 8 most significant bits are stored in ADCH. So I just need to read that particular register and I get my 8-bit precise digital conversion. Then ADCSRA has a bunch of components. First, well, we want to use the ADC circuitry, so we're enabling that circuitry. We have a prescaler, which are those 3, that we set to 128, so that we will have this 104 microsecond per conversion, and that corresponds to that 125 kilohertz ADC clock, which is within the specification that our MCU processor allows, between 50 and 200. Say you want to start an A to D conversion, then you need to set this particular position, ADSC, in this register, that bit that corresponds to that position, to 1. So that's what we do here with an OR. And then say you want to print starting ADC demo. So actually, we do that deliberately over there, because we know that that will take more than 1 millisecond. And so the conversion that we ask for in here will actually finish, because it takes 104 microseconds. Okay, so here is a while loop that we're going through, and as I said, the 8 most significant bits of the 10-bit conversion is in ADCH. We read it out, put it in A in as our variable. We typecast it to float or however you would like to do it, but this is how we do it, and we want to figure out what is then the voltage that corresponds to A in. Well, it's 256, sorry, we divide A in by 256. That gives us sort of which fraction where we are at within those quantization levels, and we multiply by 5 voltage. So we assume here that we have a 5 voltage connected to the ARF pin. Because by default, the ARF pin is the reference pin, so that's why we did not talk about it in this initialization. Alright, so now we start a conversion, and you know, about 104 microseconds later, it's done. What you want to do is you want to take this voltage that we had figured out already, and we, with this interesting library function, we convert that into a string that has 3 characters, a dot added to it, and then 2 decimal places. So in total you have 6 characters. That's why the input over here, the length is 6, and it converts this voltage, which is a float, right, into, you know, a 3-digit, 3 digits, and then a dot, and then 2 decimal places after that. Alright, now we print that over the UART, because we have linked it all up, and since that takes more than 1 millisecond, this conversion will end in time before the ADCH register is read out. So actually you need to be very careful. You need to make sure that there needs to be some delay between starting the conversion and then reading the ADCH register. So in our program right now, we just forced effectively a print statement between starting and then reading the register. Between starting, right, and then we have some delay here, and then reading again. And then starting again, some delay, and reading it again. So you would like to have at least that 104 microsecond delay. So it turns out that having such an fprint statement is enough delay for their purposes. Turns out to be. So that's what we talk about here. So it's very important that conversion needs to finish before the next conversion is called. Super important. So how can you do it? You can do what we just did. Use a print statement if that happens to fit your application. You can actually use delay functionality, because if you compute it very precisely that it takes 104 microseconds, and maybe you want to set it, well, you know, you want to make sure that you have enough time, so maybe set it to 200 microseconds. But actually, what you can do is also just implement a while loop here. So it's blocking, right? But you just got to wait. If your program requires you in your next instruction to read that high-level register, then it's probably better to just wait for this little bit of time and then go on with your computations, rather than trying to figure out whether another computational task could take some of this time to operate. Of course you could do that, but that's not how we will be proceeding here. So we have this while loop that effectively verifies when this particular position in this register is being set back to 0. Because the conversion, when the conversion ends, that position will be back to 0. Up to that point, that's not true, so it's equal to 1. So while actually this is equal to 1, in other words, the negation of that is equal to 0, let's do nothing and we wait until you get out of this while loop. So that's the kind of instruction that we will be using. So Yeah, so this is pretty much the story on ADC. And any questions about this? So you'll be playing with this. You have a bunch of tasks that you're going to work on, ranging from connecting a temperature sensor to creating a potentiometer and so forth. So next lecture we'll be talking about sleep mode a lot. So how can that, why is that useful, and why do I like to tell you about it? I'll explain. And then so this whole block that we have started right now is concentrated on ADC, and we will also start with PWM and so forth. So, well, any questions? No? All right, great. So let's go towards the lab, and then we can go from there.